Welcome everybody for this Wize Alliance webinar. So we will spend roughly 2 hours together, a little less because we are late. And the goal of this webinar is to present and to share what is Wize in terms of technical aspect, in terms of ecosystem also, and to share with you maybe the pros and cons of Wize compared to other solutions, even if it is a webinar presented for the by and for the Wize Alliance. I will firstly provide some reminders on radio frequency. What is a lead budget? What are the key factors that may or not provide an advantage for a low frequency band? So I guess you all know that Wize is using a specific frequency band, which is lower in frequency than the vast majority of applications. Then I will go through low power wide array networks. What is the concept and what are the contenders? A short focus on RF regulation, at least in Europe, even if a lot of you are not from Europe, but you will have the starting point at least. Discussing the Wize Alliance itself in terms of organization, who are we, how to join, etc. And then we'll go in more details on the Wize architecture and protocol stack. And I will finish with a view on how to design a Wize device and what solutions are available in terms of infrastructures and operators. And a conclusion with a comparison between Wize and other solutions, I'm sure you know, like LoRaWAN, NB-IoT, or Sigfox. We will have a Q&A at the end of the session. So if you have some questions in mind, even during the presentation, please feel free to type them in the chat area of Skype, and I will go through them at the end of the session. Maybe one word to present myself. And so I'm not I'm a member of the Wize Alliance, but I am from a company named Alciom. We are a design house dedicated to RF designs and antennas, signal processing, things like that, based in France. And you have to know that we are deeply linked with Wize because we are one of the co-authors of the Wize standard since the beginning. We were also deeply involved in the development of one of the key elements of the Wize infrastructure, which is a software-defined radio modem, which is used to receive and transmit Wize frames. I will go in more details, of course. And we have also quite large experience on other protocols, and in particular for LoRa, we are the training center for LoRa for France, so I will be able to share with you some aspects on these other protocols. RF basics, wow, formula. So when we are using RF for any kind of propagation, the goal is to evaluate what we call path loss, so the reduction of signal power from transmitter to receiver. This path loss is roughly two terms. One, which is here indicated as open field path loss, calculated with the formula elaborated by Mr. Fries. And another term, which is the effect of real life obstacle, polarization losses, fading, plenty of things that makes life more difficult when we are not in open field. Just focusing for the moment on open field. So the path loss in open field is basically two factors. The distance, of course. So if you double the distance, you multiply the losses by 4. Which means 6 dB if you like decibels. The other factor is the frequency, the carrier frequency. And if you reduce the frequency by a factor of 2, then you also reduce the losses by a factor of 4, mainly meaning 6 decibel. This dependency on frequency, of course, is one thing interesting for Wize, which choose a low frequency band. It's directly linked to the size of the antenna. Reducing the frequency means that the wavelength is larger, and as the wavelength is larger, the antenna is larger too. So if you have a 2.4 gigahertz transmitter, the antenna is very small, and if you have 169 megahertz, the antenna is large. And so at the same distance, the antenna grab more signal, and the losses are lower. The downside is that the antenna is larger. So, and we will see that this larger antenna is one of the drawbacks of using a low frequency band. Anyway, if we compare 169 megahertz, the frequency band used by Wize, and something more classical like 868 megahertz, then the difference in frequency imply a gain of 14 dB in path loss. So assuming that the antennas have the same performance, so meaning a larger antenna, of course, for low frequency band, then there is a 14 dB gain for the low frequency band. Okay, that's the good news. The other good news is that using a low frequency band, now this time for indoor penetration, so transmission inside a building or through an obstacle, the same obstacle has a lower loss if the frequency is lower in frequency. This is simply because the same, say, 10 centimeter wall represent a smaller number of wavelengths if the frequency band is lower. So in terms of actual figures, the figures on the left there, on the right, sorry, provide you typical things we have in terms of indoor penetration, comparing 169, so frequency for Wize, and a classical frequency band for ISM networks. For light indoor is a kitchen, living room. The losses are 4 dB lower for Wize than for 169. And for deep indoor, typically for meters, and of course, I'm sure you know that the Wize is usually used for metering application, or at least it's one of the key applications for Wize. Then the losses, the penetration losses are 10 dB lower for Wize than for other frequency bands. And that's one of the key advantage of Wize, because if you, the 14 dB I talked before regarding link budget outdoor, if you have an antenna with the same size, then this advantage is roughly lost by the gain of the antenna. However, the penetration loss is a real actual gain that you will see at the end is a key differentiator for Wize. One word on antennas, so I will not give a course on antennas, but you have to know that the antenna is probably the most critical part of any design. Even Apple lost 20% of their sales with a small antenna problem on the iPhone 4, just as an example. So the antenna, of course, must be studied in detail. And when talking about Wize, the difficulty is that there is, unfortunately, a theoretical result, which is called the Schuh-Wheeler criterion, which states that an antenna can't be at the same time small, wideband, which means easily working with variable conditions, and efficient. You have to lose one of these parameters. You can't optimize the three parameters at the same time. For Wize, the wavelength is quite long, roughly 2 meters. So a good Wize antenna is 50 centimeter long. 50 centimeter, it's not a problem for a gateway that you may install on a building, but I guess that the typical products are not 50 centimeters wide. So a Wize antenna for a device will be very small, meaning that it will be either not efficient or very narrowband. And very narrowband means that you will have to tune the antenna very precisely on any device. So the message here is that for Wize, good tuning and good optimization of the antenna is really key to have reasonable performances. I will come back on that a little later. I will skip this one. So sorry for the slide deck is very dense, so I will from time to time skip some slides. If you want to read them, you will of course get the slides after the webinar. Some words on low power wide array networks. So assume that you want to connect a device to the internet, to the cloud. How can you connect it to the cloud? The first way to do that, on the left here, what I call personal gateway, is simply to use a smartphone. A smartphone is a very good gateway to the internet, and you can have a device, connected watch, whatever you want, which may connect to the internet through your smartphone, typically using Bluetooth or Wi-Fi. This is the first solution, but of course you need a smartphone. If you don't have a smartphone, the second solution is to install a small gateway in the area you want to have coverage. Here I am writing home gateway, but it could also be a warehouse gateway or whatever gateway you want. And here you may use a protocol like KNX or Smart Mesh, Thread, whatever you want, ZigBee, to connect objects to the gateway and then to the internet. But you have to install the gateway, and plenty of gateway, because the RF coverage is quite small in terms of range. The last solution, which is called now LP1, low power wide array network, is to use a technology we provide a long range in terms of RF. And using a long range allows to put the gateway farther, of course, and the gateway may now be utilized for plenty of applications or plenty of devices, and you will, after a given time, forget that there is a gateway somewhere, and your device will be connected to the web through a long-range solution. Could be for meters or for any other applications. So this is what is called now LP1, is to use a technology which provide a very long range in order to have centralize the gateways and not small gateways in every application. The application for LP1 are very large. Of course, smart metering is one of the key applications, and we'll discuss it a lot today. Smart city is also a good kind of application. Agriculture also, tracking, industry, plenty of applications. And overall, the common factor for all these applications are that the amount of data that is transmitted is usually small, more kind of telemetry application or remote appliance, remote actioners, remote stuff, but not cameras or audio or video or Skype. And why? Sorry, I will go through my last point after. This slide is just to highlight the fact that LP1 doesn't mean going through an operator. LP1 can be used either through operated networks, meaning a network where the gateways are installed and managed by someone else than the owner of the devices, or could also be used as a private network where you buy and install a gateway or several gateways and have your private networks. These are the two vertical columns of this slide. There is also another choice. You can use either an unlicensed frequency band, a free band, or you can use a licensed frequency band, a frequency that you buy from the state. And all configurations are possible. As an example, probably you know LoRa. LoRa is using mainly 868 MHz band, so an unlicensed band, a free band. But you can have either a private network, or you can go through an operator, LoRaWAN operator, and just connect your device. Similarly, cellular operators use their 4G spectrum to provide LP1 services using technology like LTE-M or NB-IoT. And these solutions are in this area, so are using licensed band for operated networks. This solution you currently can't be used for a private network, but could be used for operated network in licensed band. And they may also be used in unlicensed band, because there are variants of this solution in unlicensed bands. So just to show that there is plenty of solutions. Yeah, thanks, Sean, for this comment. So in some countries, Wize can also, so talking about Wize, the majority of applications are in unlicensed frequency bands, but can be used either for operated networks or for private networks. I will show you some example after. And in some countries, like Australia, Wize is used in a licensed band. So going down here, because there is no probably unlicensed band in these frequency bands. So all the solution, all the LP1 solutions, so trying to go to have a long range solution, they must, in order to have a long range, they must use a low bit rate. So one of the key facts in RF is that if you want to improve the sensitivity of a receiver, you have to reduce the bit rate. That's the easiest way to do it. So all the LP1 solution, like Sigfox, LoRa, Wize, or other solution like Weightless or Ingenu, use low bit rates, couple of hundreds to kilobits per second, in order to improve the coverage. And doing that, these solutions provide a link budget which is tens of dB better than typical PC solutions or Bluetooth, but using low bit rates and not megabits per second. And you see on this graph that in the cellular world, so all these solutions there, going from classical 2G, 3G solutions to LP1 targeted solution like NB IoT, the bit rate is reduced in order to get more coverage and more deep indoor coverage. A focus, sorry for the our Australian colleagues, but a focus on Europe, just to show you what is a frequency band used for Wize. I will go quickly on this one because this specific webinar is more focused on far parts of the world. So in Europe, we have a recommendation which is called REC ERC 7003, which states which frequency band can be used for unlicensed short-range devices. And Wize is considered as a short-range device in terms of regulation in Europe. The Wize frequency band, 169 MHz, is defined in for two kinds of applications, which is called non-specific short-range devices, Annex 1, and tracking, tracing, data acquisition, mainly sensors, meters, things like that, which is another annex. To make things short, for these two annex, both specify that the frequency band that could be used is 75 kilohertz in these bands at 500 milliwatts, so which is quite huge transmit power. The only difference is the duty cycle. So for metering application, 10% duty cycle, meaning a 10% transmit time is possible. For other application, it's limited to 1%. The good news is that this regulation then protect the metering application because they could use the band with a larger duty cycle. And in terms of European countries, so the frequency band in question is usable in all European countries except Russia. And in other countries of the world, so there are usually bands close to 169 available with different regulations that may be close or not, but except the US, maybe there are frequency bands everywhere close to these frequencies. So, Wize Alliance, everything started in the early 2000s with firstly a protocol, another wireless protocol, which is called Wireless Bus, which was designed for industrial automation purpose and home automation or domotics applications using 400 and 800 megahertz bands. This wireless bus, I will talk about wireless bus, but the actual name is EN 13757.4, which is an European standard, an official European standard now. Independently, there was an application named Hermes using the 169 MHz band. Hermes was a pager application. So using this band to provide low power, very wide coverage paging applications. And soon after that, this paging band was used for opened for metering applications. And Suez was the first company to use this band to develop water measuring devices in 2008 using this frequency band. Then things started to have a far wider use case range in 2012 when GRDF, so GRDF gas distributor for France, decided to use the same technology for gas meters. And they decided to join with Suez to develop jointly the same technology and to move from a simple water metering device to a full features protocol stack that is now Wize. At the same time, it's important to note that Suez and GRDF decided to join regulatory agencies, in particular AFNOR in France, linked to EN and CEN, to bring this Wize protocol stack to notification bodies and to regulation bodies in order to stay as close as possible to the EN wave assembly standard. 2014, the Wize specification was written by Suez GRDF, but joined by other companies, Sagemcon, Deal, Kirlink, and ourselves, Alciom, and Itron. And jointly, we wrote the specification and also developed the infrastructure, so the carrier grade concentrator gateways that I will present just after, and of course, meters compatible to the protocol. So Wize Alliance itself was born in 2017 with the release of the specification, which is now public, as you know. And now, a couple of years later, we are very happy to let you know that we have 10 million Wize meters on the field. We'll provide you more information at the end of this session. 10 million devices, so maybe one of the largest IoT network, or at least one of the largest network with a single operator and mainly metering use case. The Wize Alliance members today, so we have 30 members or so. So they are split in different categories depending on the involvement on the Wize protocol. But you see the name. It's always interesting to know who are the actors of such an association. So of course the historic leaders are there, but also silicon suppliers like ST or Synapse, module vendors like Radiocraft, we'll talk about them later, software companies, universities, startups, plenty of companies around the Wize association. We'll skip this one. So if you want to join Wize, you have to know that, of course, there is a contribution. If you want to be a regular member of the Wize Alliance, you have to pay 3,000 euros per year, except if you are institutional or startup, and then it's free. And if you want to be active member, which mainly means that you will be able to contribute to the Wize standard and access to the draft specification, then this is 10k euro per year. And if you have to be executive, it's a little more expensive, but probably it will not be your case. The key deliverable of the Wize Alliance, of course, is the specification itself, now in version 1.1. So the specification is fully open, available on the web. Everybody can download it. And starting from version 1.1, the specification is split in 3 documents. The main specification itself, and one regional parameter document, which basically contains everything linked to a given region of the world. So frequencies, channels, allocations, things like that. And another document, which is the common application layers, which defines the application stack. I will talk about that a little later. So the three documents make the Wize specification. Regarding the architecture of Wize, so I will, in a first step, provide you an overview, a big picture of what is Wize and how the messages are transmitted. And then I will go into a little more details on some aspects. And we'll finish and discuss with the hardware. So the first things to know is that OSI model. So everybody which has one time looked at something on telecommunications knows that now for 40 years everybody is using the OSI model, but nobody is using it. But anyway, the goal is to split the protocol in terms of layers of different abstraction levels. When you go down, low-level layers are close to the physical way of transmitting bits of information. And at the top application layer is actually the semantic of the data transmitted. Wize is using for the low-level layers wireless M-bus, so the actual wireless M-bus standard, without any modification. There are some say precisions provided in the specification, but we are fully compliant with wireless M-bus. More exactly, wireless M-bus is a protocol which defines a standard which defines plenty of different modes, T1, T2, R1, R2, C1, etc. And Wize is using one of the modes, which is called N2. And Wize, the wireless M-bus N2 mode is the actual layer 1 and 2 of Wize. So nothing specific there, and you will see that this low-level layer provides 6 channels of 12 kHz each, and then on top of this low-level layer, the Wize protocol will define a way to encode the message in order to provide a bidirectional communication with packets of up to 128 bytes and a little more and twice more in the downlink, and to manage different bit rates going from 2,400 bits per second to 6,000 bits per second. And we'll see also that a huge part of Wize is the security, and Wize is providing a secure way to transmit messages back and forth between devices and network. In terms of architecture, so the Wize architecture is made of gateways, devices, LAN modems, and head-end. So device is anything on the field, say meter, and you will be right 99% of the time, but it could be, of course, anything else. So a device is on battery and can live for tens of years. A gateway is something installed usually on top of a building and providing Wize coverage to a given area through what is called LAN modems in the Wize denomination. So a LAN modem is a radio unit which provide an antenna and can communicate to devices. And a gateway can have one or several LAN modems. Usually, a gateway could have, for example, 2 or 3, 4 modems installed on different sides of a building, for example. And then the gateways are connected to the head-end, say computer, server, whatever you want to call it. And as soon as we leave the gateway, we are in the IP world. So the gateways could be connected to the head-end through any IP compatible solution, usually 4G, but could be anything else. That's the big picture. In terms of message flow, how does it work? a device can send a message whenever you want, and a message sent by a meter is always sent in broadcast mode. So meter just broadcast a message. So a meter usually sleeps every time, wake up whenever you want, and transmit a message in the air using Wize protocol and using one channel at random if you want, and one modulation at random if you want, or one modulation pre-programmed by the network if so. The gateways are all listening to all channels and all modulations, and will receive the message from the meter. The same message from a meter can be received by two gateways. The gateway, in terms of security, will do a first security check of the message, which show how it's working. And if the message is considered as a valid Wize message, they will transmit the message to the head end. The head end process the message, and if there is a need to transmit back a message to a device, the head end will select a gateway, send in a message, and ask the gateway, please send this message to the meter. We see that the meters have a receive window, which they are able to receive a message from the head end. That's the usual way messages are sent back and forth in Wize. And there is a last message flow, which is multicast, that allow the head end to send the same message to several devices at the same time. This multicast mechanism will be used for over-the-air upgrades, and I will talk about that a little later. LP1, there is LP low power, so we need to have a way to reduce drastically the power consumption of the devices. And Wize do that using very strictly defined timing windows on the device side. So the device wakes up once again whenever you want and transmit a frame. A transmission in Wize is usually around 100 milliseconds for short messages. Then the device go back to sleep for exactly 5 seconds. And after 5 seconds, he wakes up again to listen to a given channel for a very short amount of time, 20 milliseconds. The device, the network, and in particular the gateway, knows that the device will receive 5 seconds after. So the message is sent to the end, and if there is a need to transmit a message to the device, the gateway will transmit the message exactly 5 seconds after the transmission from the device. And then the device will transmit an acknowledgement, and so things will go on. This way allows the current consumptions linked to the receptions to be very low compared to the overall consumptions of the device, and this possibility to have a downlink is roughly 10% in terms of energy compared to the full transmission energy of a device. So 10% is roughly acceptable to have a possibility to talk to a device anytime. For those who knows LoRa, this is roughly the same concept as the one used for LoRaWAN, same kind of efficiency. However, for those who know Sigfox, this solution, Wize is far better than Sigfox in terms of energy management for the reception windows. Yes, so I saw the chat, so all questions will be answered at the end, but we note them and we will try to go through them at the end, if you don't have already the answer. Okay, so in terms of protocol stack, so the low-level layers of Wize, once again, are wireless and bus standard. And we define on top of that a presentation layer, which will be mainly linked to security. I will go into a little more detail. And on top of this presentation layer, you will be able to use any application layer. And Wize will define three mandatory application layers called here app install, app admin, app download, which define the common behavior we expect from any Wize device. App install will be for commissioning of the device, app admin for remote configuration of the device, and download for over-the-air programming. And then any device will be able to implement an end-user targeted application layer. If you are a gas meter, then the Wize Alliance provides a standard application layer for gas meter. Same for water meters. And if you design something else than a gas or water meter, you will be able either to use app admin, which could be used for an end device to do anything, or you will be able to design your own application layer, either as a proprietary application layer, or you may submit to the Wize Alliance a proposal for a new application layer. If you want to design a connected street light using Wize, you may design an application layer for that. It could be quite simple, and you may use it. Let's skip this. Regarding looking at the hour, yes, so we started late, so I'm late, but it's normal. Regarding the Wize protocol, some more details on the protocol itself. So in terms of low-level layers, so wireless and bus, there are 6 channels once again, and 3 different modulation are supported. 2400, 4800, and a modulation named high speed in Wize, which is 6400 bits per second with a quite more complex modulation. And at the bottom of this slide, you have the typical performances, typical conducted performances, so without the antennas, that we have on usual Wize devices. So the transmit power is usually 500 milliwatt. 27 dBm, and the sensitivity of the device for a device is roughly minus 120 dBm, and on the infrastructure side, the sensitivity are far better because we have a more complex receiver, and we are from minus 120 to 126 depending on the bit rate. If you calculate the corresponding path loss, we are from 146 to 153 dB path loss, and you may say, okay, what does it mean? So what is the coverage I can gain with 146? At least even talking the worst case here, 146. What is the path loss? If we look at the formula, and you say, okay, I'm at 169 megahertz, and I have this 146 dB path loss, what is the coverage I will have? Even taking into account not so good antennas, so here I assume the device antenna gain of minus 8 dBi, which is a small antenna for Wize, and a typical not so large antenna for gateway. Then if you calculate the path loss, you see that you can, in open field, theoretically go up to more than 1,000 kilometers. And it is actually the link budget that you may have using this frequency band. If you have not any obstacle around, you are in the middle of the ocean, you can go up to 1,000 kilometers, which is the coverage you have with maritime radio, for example. If you add some extra losses for indoor penetration, say here 25 dB for penetration loss and 7 dB more for fading losses, you do the calculation, you find out that you may go up to 30 kilometers even in deep indoor. Of course, it's theoretical, but 30 kilometers seems still quite significant performance. And you may ask, is it real or not? So I've asked my dear colleague from GRDF to provide us some actual data. So this is the actual coverage of a rollout of GRDF in Le Havre, in north of France, for only one concentrator. So there is one Wize concentrator, which is located here. And the small color dots are meters, which are in a wall, in a side of a building, or in a first ground level of a building. And the colors show the reception level, and the light blue are the worst one, which are minus up to minus 120 dBm, which we have still 5 dB margin compared to the sensitivity of Wize. And you see that here the scale is 8 kilometers here, so we have roughly, say, a 5 kilometer area with a good coverage indoor for metering applications. So that's still not so that's not 30 kilometers, but you will see that typically for rural environments, 10 to 15 kilometers is usually what we get in Wize with deep indoor. That's so all the field tests show that it's significantly better than the other applications, the other LP1 protocols for deep indoor, at least when considering protocols like LoRa or Sigfox. And I will provide some comparison at the end. Okay, that's the wireless and bus frame format. I will skip it, it's wireless and bus. And Wize will add, so we'll define this of protocol. Okay, we have wireless and bus, and how do we code the actual information? That's what Wize will provide in terms of spec. And Wize will add a couple of fields. I will not go in detail on this field, but mainly all the things that are circled, so this one, plenty of the fields, or even this one, are dedicated to security. So I will go a little more in detail on the security aspect of Wize, which are basically the added value of the layer 6 stack of Wize. Security is of course a key element for any LP1 or any wireless protocol, any protocol. And Wize is implementing a 2-layer security using 2 different keys, security keys, one called KeyMac and one called KeyInc. There are a couple of others, but they are the main ones. KeyMac is a key which is shared for a full network currently. So the same key for all devices, and the same key is known by every gateway on the network. This first key is used as the first level of defense in order for the gateway to check if a message is coming from a device which seems to be a regular Wize device. As the key is shared for all devices, of course, it's not a public key. It's a key that is only communicated to Wize operators and device makers. But in order for the gateway to check the key, the check is very fast. Then there is a second level of defense, which is the actual security of Wize, which is managed by the key programmed on every device, and a private key for each device. It's not the same key for every device. And this key is also programmed on the head end, so at the other end of the communication. And this key will be used both to authenticate the frame, to verify that the integrity of the frame is not modified, so that anyone can't modify a byte in the frame without knowing the key, and will be used also to cipher the content of the frame. These keys, the Wize protocol provide up to 14 keys pre-programmed in the device, and there is a safe way for the head end to change key in case of a given key could be compromised by anything. So it's both a way to protect the information and to protect the loss of a key if a key is jeopardized. Wize is using AES in terms of safety ciphering protocol, currently with 128 bits keys, and everything is planned to go up to 256 keys, 50 bytes keys if needed. Okay, so I will not go in full detail there. You have to know that so the first step is a ciphering. So the information is firstly ciphered using the private key Ankh key, and then Wize calculates an hash code, so a signature of the message using the same ciphering key. And another hash code is calculated, hash kamak, is calculated using the second key. And the gateway that will receive the message will firstly check these 2 bytes here, knowing the kamak key. And if these 2 bytes are correct, okay, that means that either the sender was actually a regular authorized device, or maybe he sent 65,000 messages and just one got the boot key by chance. But anyway, it reduced drastically the charge, the load on the one protocol. And then the second layer of defense is now with 128 bits key and hash code, which is these bits here, and that will be checked by the head-end system for full security. Once again, for those who know LoRa 1, it's roughly the same things between Wize and LoRa, but LoRa copied Wize because we wrote the Wize protocol stack 2 years before LoRa 1. It's roughly the same thing. The difference is that in LoRa 1, the authentication with this KeyMac key is done not by the gateway, but by the network server. So there is no security in the gateway for LoRa, rather than for Wize, there is a first level of security managed at the gateway level. That's another engineering choice. Let's keep that. So in terms of application layers, so one of the common application layers that must be supported by every Wize device is called AppAdmin. AppAdmin is a very simple protocol, application level protocol, which allows the head-end to send a command saying read or write this parameter with any kind of parameter you want. So you may have your own parameter table. For example, you want to design, I don't know, a light sensor, and the head-end may use AppAdmin to send a command read parameter and with the address of the parameter, which is a light sensor. You can also write parameter. Say you want to design an actuator, you want to connect to switch on and off the light, you may send the right parameter and with the light level. This AppAdmin protocol is also used internally for Wize in order to configure the devices. For example, the transmit power or the modulation and the available channels are programmed by the head-end using the same AppAdmin command and with a table of parameter which is standardized by Wize. And if you look at the common application layers document, you will have a full table, just an extract here, with plenty of parameters which must be implemented by all Wize devices. The second application layer, which is mandatory for all Wize devices, is called app install. App install is an application layer which allows an installer, a commissioner, to check the connectivity with the Wize network when installing a meter somewhere, a device somewhere. This specific application was designed to be managed directly by the gateways, which means that for a new Wize network, it's possible to install the gateway, and even if there is no fully functioning head-end, then you can test the configuration and the connectivity between the meters and the gateways using this protocol. Basically, the meter sends a ping message, and the gateway responds with a pong. Okay, I got you. And you have the SSI, you have everything you need to check that if you are in connection with one or several gateways. The same AppAdmin protocol, so the one I talked before with a table of parameters, is also used by the Wize architecture in order to correct for a given Wize device its clock and its array frequency. So any Wize device must allow the head end to correct its clock and its array frequency if it is drifting over time. This allows to design, of course, a low-cost Wize device because you can use a low-cost crystal. And if the time of the day or if the array frequency is slipping, is moving too far from the theoretical frequencies of clock, then after a given time, the architecture, the network, will send a message using AppAdmin saying to the device, hey, please go back to this time, or please increase your array frequency by 200 Hertz because you are moving too low. And this is supported by the architecture, by the protocol. And the protocol stack doesn't specify if the algorithms must run on the head end or gateway or anywhere else, but it specifies the protocol, so the messages that a Wize device must process in order to allow this correction. And in particular, the same applications, the same kind of messages is used by a Wize network in order to optimize the network capacity using downstream AppAdmin messages in order to configure a measure, a device, with the optimal transmit power and bit rate depending on their position on the network. So, for example, Wize allows the head end or gateway to find out that a given meter, for example, this one, is very close in terms of link budget to the gateway, and then could send to the gateway, to the device, a message saying, hey, I heard you loud and clear. Please reduce your transmit power by 10 dB, or please go to high-speed modulation in order to limit the occupation of the network. And this allows to optimize dynamically the configuration of the network through an algorithm running on any node of the network. Once again, for those who know LoRaWAN, this is roughly the same idea as adaptive data rates, which is put in place on LoRaWAN networks. Same issue, same solutions. And the last, but not least, solution provided by Wize protocol stack is over-the-air upgrade. Of course, a solution like Wize is designed to support millions of devices on the field. And if you have to upgrade the firmware on the devices, you can't send the firmware to every device separately. It would take years. So you need a way to broadcast the new firmware to a set of devices. How is it working? So the first step is that the head end usually will decide which devices have to be upgraded and have to receive the same firmware, usually with serial numbers and things like that. It will then generate a list of devices to be upgraded and will decide which gateway should be used for the broadcast based on the connectivity map it knows between the gateways and the meters. The manufacturers of the devices will provide the software to be sent to the devices, and this software will be split into small chunks, and the Wize protocol requires the chunks to be smaller than 210 bytes. Okay. Then, in the second step, invitation step, the network will send to every device to be upgraded one by one a message through this message is called announcement download announcement, and the message roughly states, hey Meter, I will broadcast a new firmware for you. This broadcast will be done on channel 3 tomorrow morning at 3 a.m. And then please note that I will broadcast again the same firmware the next day and the day after. So these messages are sent far in advance to all metters, and at the good time, all metters will wake up and will listen to the channel to receive the broadcast. They will get probably a significant number of chunks of the firmware, and if they don't get all the chunks, they will wait for the next broadcast and will receive the missing chunks. When they will have all the chunks, they will upgrade themselves using a bootloader protocol, something like that, and they will reset, start again, and will send to the network a confirmation message saying, "Hey, I'm upgraded," and that works. So there are plenty of details, but just looking at the last line on this slide, you have to know that this protocol is actually working, and in particular on the GRDF network, it was used a couple of times, and on tens of thousands of devices, so it's not a small test. And the test showed that on the first broadcast, 99% of the metters were upgraded the first broadcast. So that's a quite nice achievement. Of course, I've not indicated that, but the fact to be able to have a remote upgrade of the firmware is the best solution to ensure safety of the communication, because if there is a flaw in the protocol, a safety break, for sure someone in the future will find a break somewhere, then we have a way to upgrade the metters. Okay, so there is a specific frame format for upgrades. The only key difference is that for upgrade, there is an error correcting code which is added to the frame in order to improve the transmission rate from the infrastructure to the metters. That's managed by the protocol. Okay, so Wize is now in version 1.1. We used to have a version 1.0. The differences between 1.0 and 1.1 are roughly minor. And you have to know, of course, that the Wize Alliance is still working on new versions of the protocol. And there are plenty of good things in studies or in standardization phase right now. The first thing is new modulation formats. So it's not new. We have already worked now for 3-4 years on new modulations, far more advanced modulations, to have an extra penetration for ultra deep indoor. And we have currently on the networks modulations which provide 8 dB improvement compared to the current Wize protocol that I've described up to now. These modulations, of course, are not part currently of wireless and bus standard. So they are tested on the network today, but they are not yet in the Wize standard because we have to go through standardization through the wireless and bus bodies in order to standardize these and to put them in the Wize protocol stack, and to open them. Same for downlink. We have advanced modulation studies to improve the downlink link budget for deep indoor. In 2020, so this year, we have also huge works ongoing in the Wize Alliance to support more flexible network infrastructures, and in particular to support virtual networks. The idea is to be able to have several applications, several class of customers on the same physical network, but with segmented security and segmented flows. This is also linked with roaming support, so the fact to be able to move from one network to the other with security aspects that must be upgraded in order to support that. So that's work ongoing. If you are interested in this work, so please contact the Wize Alliance. You will be more than welcome to participate with that. We also have some works ongoing regarding wireless M-Bus. So the wireless M-Bus spec was upgraded now a little more than 1 year ago. And the Wize protocol is still based on the previous versions of wireless M-Bus. So we have an alignment work ongoing, not so simple. And lastly, we have in mind to work on evolution of the Wize protocol stack to support walk-by and write-by application. So maturing through something else than fixed gateways. And this will be integrated in Wize without probably any hardware change on the meters. Still work in studies. That's it for the Wize protocol itself. I will spend a quarter of an hour to discuss about infrastructure and devices, and then we will do some synthesis and go through the questions. Firstly, in terms of hardware, like a cellular network, for example, a Wize solution is usually very asymmetric, meaning that there is a small number of gateways compared to the number of meters. A typical metering project will have millions of devices, but only thousands of gateways. So the technical solutions usually used for gateways and meters are not the same. Meter has to be very, very, very low cost and very, very, very low power, but usually is not very critical in terms of RF performances, in particular in terms of immunity to strong fields. Rather, for gateways, it's the opposite. A gateway may be more expensive because they are, of course, lower in count, but must have the best possible performances to limit the number of sites. And the RF constraints in terms of gateways is far more drastic because they are usually other high power transmitter close to the gateways. So we'll go firstly through the meter solution. So if you want to design a Wize compatible device, the first solution will be to use a chip, an RF transceiver chip. I've shown there some silicons that are actually used by meter suppliers from Texas, Analog Device, Silicon Labs. There are plenty of other solutions, but at least these chips versions are currently used in millions of units on meters. Chips cost, say I put $2 to $4, but if there are budgetary prices, if you look at generically accessible catalogs for 1,000 units, you will probably pay them far cheaper if you go for an actual project with larger quantities. So this is roughly the same cost as a typical 800 megahertz chip. The only extra part in terms of electronic needed for a Wize device is a power amplifier, which is called a front end here, which increase the transmit power to 500 milliwatts. The typical chips for that are sold by companies like Skyworks and cost $1 more. So if you, I will not go, of course, in detail of the schematic, but if you have a look at the schematic of a typical device, all the parts on the left side here are the same, exactly the same if you have a LoRa or a Sigfox device and a Wize device. You have a microcontroller, you have a transceiver, a crystal, maybe some flash for over-the-air upgrade, and power supply. So all these parts are common for any connected device. The extra part for Wize is what is on the right side, so which is high power transmitter. So you see that roughly you have say, 20–30% more complexity for Wize, and so $1 more for Wize in terms of electronic parts. Okay, is it too much, I don't know, but $1. But hardware is only a part of the problem. Then you need the stack. You need if you buy a chip, say, assume you buy one of these chips for the silicon supplier, you put the chip on the device, you will have to code the actual Wize protocol stack to implement the protocol. What are your options? Currently, so today, you have 3 options. The first option is to code the stack yourself. This is actually the solution used by the vast majority of devices today. Companies like Dell, Sagemcom, Itron have developed their own Wize protocol stack based on the protocol published by the Alliance. But based also, you are not starting from zero because the chip vendors provide usually the low-level layers, wireless and bus stack, provided as application note or reference design by chip suppliers like Texas Instruments or Silicon Labs. But you still have to code the rest of the protocol, security, download, everything. That's a significant amount of work. The other solution that you can use today is to go to Suez, and Suez is providing a full stack running on Silicon Lab EFR32 system on chip, and it's available today. The model for this solution is the following. So the stack is provided with a freeware license, at least if you don't need to use the water metering application layer. This water metering application layer is under royalty, okay? But if you want to develop a generic product, the stack is free of charge, but you have to buy a specific version of the chip through Arrow France, which is a distributor of the chip. So you buy the chips through them, and the chips are pre-programmed with a key which allows you to use Suez protocol stack. And then if you need to have professional service support to use the stack, but then of course Suez Smart Solution, which is an entity of Suez Group, will be able to support you. I will just show you one slide on that. So the stack is provided today. Some methods are using it, some reference design are using it. You can use the stack using Silicon Labs demo boards, and a dedicated metering application development kits is under development by Suez and will be available soon. The last solution is using open source Wize stack developed by GRDF. This will be a fully open stack, so provided without any limitation and in full open source. However, the stack is still under development and will be available in Q3. So you will have to wait a little. This stack will be initially provided running on STM32 microcontroller from ST, and with an RF chip from Analog Device, ADF7030. The accompanying hardware will be provided as open source hardware by Alciom, and we'll show you that in a minute. But okay, so good news is that it will be fully open. The bad news is that you will have to wait a little. If you want to have more information on this solution, of course, contact the companies here, so GRDF, Alciom, Suez, whoever. Or contact, once again, the Wize Alliance, which will direct you to the good people. If you don't want to use a chip, but if you want to go quicker to the market, you also may use a Wize module. So a Wize module is something that integrates all the RF microcontroller, but also the Wize protocol stack. Currently, there is one vendor of Wize module, which is Radiocraft. Radiocraft provides modules now available on the market for 1-2 years. These modules are provided in two versions, RC1701, RC1702, based on the different, application framework. For the first version, so 1701, is a fully included Wize module, which means that the stack is on the module, and you have an external microcontroller talking to the module, usually through a UART link, and saying to the module, hey, please send this message using Wize. And the module is doing everything else. The second version, 1702, is a more open platform on which you can run the Wize stack, but also your application if you want, or if any specific Wize application you want. And on this second version, you may develop over-the-air programming if you want, and not on the first one. These modules are available either directly from Radiocraft or for small quantity through distributors like DigiKey, and you have on the right the public prices provided by DigiKey for such modules. You have also to know that so of course Radiocraft is providing evaluation kits for these modules with everything you need, antennas and everything else. Another solution is to buy evaluation kit or Arduino compatible baseboards from another company, Wize, which is also a member of the Wize Alliance. These modules are using Radiocraft modules, but another form factor, another software framework, and could be also used for, say, proof of concepts, for example, using an Arduino base, maybe a good solution. That's it for the modules. So the last module, the last possible solution you will have in the near future is the Wize Up module I talked about when I talked about GRDF OpenStack. So we, Alciom, are developing jointly with GRDF another Wize module, which is called Wize Up. And this module will be the hardware base for the GRDF open source stack. And the module will be provided in open source hardware fashion, mainly meaning that the module schematic and layout and everything you need will be fully open and provided by us freely. You will be able to copy and paste the module schematic or even to reproduce a module yourself. We also sell the module, the fully assembled module if you want, and provide any customization service you may need. That's the good news. The bad news is that the module is not available yet. It will be available at the same time than the open source Wize protocol stack by GRDF. So Q3. For any information on that, call us. Antenna. So I've already talked about antennas. Just to remind you that the antenna is a significant part of a device development. And one of the difficulties that you will encounter is that as the device is small compared to the wavelengths, you will be wrong if you think that a Wize antenna is a component that you screw on your device. Your full product will be the antenna. Even if you have an antenna and a connector, as the product is small compared to the wavelengths, you don't have a large enough ground plane, and the full product will radiate. So when you are discussing Wize antennas, except if the product is very large and using dipole, but it's usually not the case, then the full product must be designed to be an antenna. And so the message here is don't wait too late to design the antenna. The antenna design should be done at the same time as the product concept phase, very early in the design. If not, you will probably have a very the worst possible antenna. Of course, if you want to design your own Wize product, you can do it yourself, or you can call Wize Expert Design House. A couple of them are on this slide and member of the Wize Alliance. All this company can help you with your designs. And the Wize Alliance, of course, include also off-the-shelf module, off-the-shelf product developers and resellers. If you want a water meter or gas meter or a trash can level meter, there are already some companies who develop and sell products, so you don't have to design them from scratch. Just call them and they will sell you the product you want. A last word, so GRDF also an example. So GRDF has developed a universal transmitter. It's an example of a Wize device, just to show you a picture of full features. So it's a quite complex one with plenty of input, outputs, even a GPS and shock sensors and plenty of things. But to show you that on such a design, so if you remove all the connectors, if you remove the GPS and even RFID here, and then you have roughly the size of a Wize transmitter, and you see that here in this case it was a dipole antenna made on the side of the device, which was included. An example. That was for devices. Just one word for the infrastructure side. So the Wize Alliance members designed carrier-grade infrastructure elements, in particular for the gateways. And you have here an actual picture of a Wize carrier-grade gateway, which is the box on the left here. You have roughly a central unit with Linux running on, and 4G network connectivity, power supply, plenty of things. And you have so a modem, so the RF modem, which is here and opened on the right side, which is a high performance software radio based Wize communicator, which is very specific for this kind of receivers. Is that this modem is receiving at the same time the 6 channels with all modulations, and it's upgradable, so plenty of things. So we were Alciom. We are very proud to be one of the developers of this radio modem. And you have to know that these concentrators are manufactured by 2 companies, Sagemcom and Kerlink, on behalf of Suez and GRDF. So the model is that the design is owned by GRDF and Suez, and the manufacturing is subcontracted to Sagemcom and Kerlink. This means that if you want to roll out your own carrier-grade infrastructure, you may develop it yourself. Or if you want to buy this concentrator, you have to go to Suez and GRDF. That will, of course, be fully open to let you buy them under transfer agreement to be negotiated with them. So the contact point is Suez or GRDF to buy the infrastructure. If you want to develop a small network, you don't need to have a full performance carrier-grade infrastructure, but you want to roll out a small network for a factory maybe, or a demonstration network, then you could also use a module from Radiocraft to develop the gateway. So Radiocraft modules could be used as a gateway. Single channel, single modulation, and little lower performance gateway, but gateway. So you can do that either using RC1701 module from Radiocraft and with the corresponding baseboard, or you can use a variant of the same module sold by Allwize as a Wize to Wi-Fi gateway. It's a small product, €50 ship. Using, of course, Radiocraft modules and providing a connectivity, Wize connectivity for small networks. So not all the features of a Wize protocol are supported. You have only one channel, you have not over-the-air download, you have not frequency hopping, plenty of things that are not supported. But anyway, you can demonstrate and provide a small Wize connectivity solutions using either the Radiocraft module alone or such product from Wize. For any additional questions, just call Radiocraft or Wize. I'm sure Peter, which is on the line, will provide his contact name on the chat in a minute. Regarding operators, so currently, so I told at the beginning, we have already 10 million devices on the field, mainly on networks owned by Suez and GRDF, and covering not less than 10,000 cities in a couple of countries. I'll show you a map just after. Of course, if you want to have your own, if you want to have a coverage, a Wize coverage in another country, you can roll out your own network, fully private network. You can also ask one of these operators to roll out and manage a network for you. It's an operated network model. Or you can look at a hybrid model mode, which is proposed by, in particular, Suez, where you will install and own your gateway, but subcontract the management of the network to Suez, for example, or GRDF in another country. I will show you some more information for these two networks, and then I will show you an example of a private network or hybrid network model in France. GRDF is probably today the largest network in terms of devices. 5.5 million meters are already up and running in France using the GRDF Wize network with 7,000 gateways installed on the field. 80% of the population and 77% of the territory are already covered by the Wize network of GRDF. And the rollout will finish in 4 years now, 3-4 years, with 11 million devices and 12,000 gateways. So every house in France will have his gas meter connected through Wize. You have to know that GRDF has launched a dedicated subsidiary named IO with me to manage the Wize network and to manage the connectivity service. So if you want to contact GRDF and to ask them if you could use their network for your application, then the contact is IO with me. Contact is Alain Descendré, which is on the call, and or through the Wize Alliance once again. Suez is the second nearly as large player. I have to go to say that, because if not, I will be honked by one of my customers. Suez has today 4.5 million devices in Wize on the field, 2.5 million in France, but not only, 1.6 million in Spain, and some thousands units in Malta, Portugal, Czech Republic, and other countries. So a couple of other countries where we have pilots today. Of course, as we have someone from Australia, I guess that the full Australia is not covered by your Wize network today, but maybe sometime. Australia is large, but at least we have pilots in several countries over the world. China also, Polynesia, New Zealand, Africa, North Africa. So Wize is running up and will take some time to be worldwide, but we expect to have networks in several countries. Suez, talking about Suez, provide two offers in terms of services, either just transmission of information, so going up to layer 6. So basically, they will take care to deliver you the data, and you manage the data as you want. Or they provide also an added service, which is the collection and management of water or environmental data, providing full features, web server, application server to manage the data and to manage alarms and everything else. So these two kinds of services are available through through Suez. Another example that I found interesting to present you, a smaller network, just to show you what it could look like for a medium-sized Wize network. So talking about Regaz, and more specifically Bordeaux Métropole Energies, which is a gas distributor in Bordeaux, France. So Bordeaux is a very nice city for those who are not French, which is in the west part of France. Very good wines in Bordeaux too. Regaz launched a network to monitor some tens of thousands of meters. And they were kind enough to share with us the schedule of their project, which may give you some ideas of what is a typical schedule for a Wize network. So they started with, of course, preliminary studies and proof of concept, which helped them to decide to go for Wize in mid of 2008. Then they started to select and to integrate the head-end and to negotiate the sites for installation of the gateway. Site negotiation is always a nightmare in every cities and every country, because you have to find the sites, to negotiate with the owner, to bring power supply and everything. So roughly this took 1 year of preparation of site negotiation before the start of the actual rollout. And now we are 1 year of rollout, both for meters and gateway. And after 1 year of rollout, this is the status. So 40 gateways are installed and 47,000 meters are installed. On these 47,000 meters, more than 45,000, so 96% of the meters are already connected. So this means that without any network optimization to date, just installation, already 96% of the meters are connected from scratch after 1 year of rollout. So seems to be a nice achievement. And the map also is interesting. So we don't have the scale, sorry, on the map, but from, for example, this large area here is maybe 10, no, little more, 20 kilometers wide. So 20 kilometers here, and you have ici also maybe a little more than 10 kilometers, 15 kilometers there. So these two gateways are more than 15 kilometers apart, and you have meters here that are connected to the network. So the coverage is significantly larger than 10 kilometers. And here the network is denser because Bordeaux is a very dense urban area, so the meters are deep indoor. That's why there are larger number of gateways in the area. So seems to be interesting things to share. That's it. I will just finish up before the Q&A by I say 5 minutes of synthesis. So we'll have time to read the slide, but what I wanted to do there is to compare Wize with LoRa, NB-IoT, and Sigfox based on link budget, energy, and more globally. Of course, this kind of comparison is very critical. We can spend hours to discuss the hypothesis. What I want to know, to let you know, sir, is that I'm targeting deep indoor, typical metering application. So I've selected a 20 bytes message with deep indoor coverage and comparing this solution in this specific case. And yes, also I took in as an assumption that the full bidirectional link is needed, meaning that I want to be able to send a message to a meter every time he talks to me. That's one of the hypotheses. So if we compare in these hypotheses the different solutions, so we'll not go through all the figures, but just looking at the colors here. So LoRa, Sigfox, Wize, and NB-IoT. In terms of link budget and with some hypotheses, when we are in free space, so the first line here is a free space performance, all the solutions are roughly equivalent. So Wize is maybe a little lower in performance for the downlink compared to NB-IoT or LoRa, but quite similar to the other one, minus 160 something dB. uplink, nearly all the solutions are equivalent. However, if we look at indoor and deep indoor performance, then for us, for sure, Wize is significantly better, say 15 dB better than LoRa or Sigfox, and better, roughly 5 dB better than NB-IoT, with the hypothesis I took. So for us, the key advantage of Wize is deep indoor penetration. And the only real competitor will be NB-IoT, more on that later. In terms of energy, so battery life, using the same kind of assumptions, for us, honestly, LoRa is the best one in terms of energy, but Wize is close. So here we have an evaluation of the total energy per message in milliampere seconds per unit. So LoRa 36, Wize 45, okay, a little more, but same order of magnitude. In this specific use case, Sigfox is more than 10 times more power hungry, use the battery 10 times more than Wize or LoRa, mainly because the frames are longer than 12 bytes, and this Sigfox is limited to 12 bytes. Sigfox is repeating every message 3 times. And the downlink is very, very, very power hungry in Sigfox in this specific use case. NB-IoT, it's a little more complex because NB-IoT, so the cellular solution, 4G solution, the power consumption is very dependent on the module, the kind of module you are using, and very dependent on the network configuration, the operator choices. Worst case, 600, so nearly as bad as Sigfox. Better case, so using the best modules we found and using the best configuration, we are, for us, roughly 2 times more energy hungry for NB-IoT than Wize or LoRa. So for the moment, NB-IoT is still not as good as Wize in terms of power efficiency, but we have to take care as a Wize Alliance because it may change over time and NB-IoT will become better. But for the moment, Wize and LoRa are the best solution energy-wise. Okay, and then I try to put an overall figure. Okay, what is the best solution for which application? And I try to be as honest as possible. Have a look. Outdoor link budget, okay, don't worry, every solution are good. Deep indoor, Wize is the better. Maybe NB-IoT is a little more green than the other ones, but Wize is for sure the better for deep indoor. Bidirectional link budget. The best ones are LoRa and NB-IoT. Wize is a little worse in terms of downlink. So in LoRa or NB-IoT, if you have an uplink, you have a downlink. In Wize currently, if the meter is very, very, very deep indoor, you may have uplink, but not downlink. We are trying to improve it, but that's the status. Sigfox is even worse than Wize. And battery-wide, Sigfox is not compatible with bidirectional all the time. Low energy, so for example, for the moment, Wize and LoRa, the best one, Sigfox and NB-IoT are not as good. Over-the-air upgrade, Wize and NB-IoT provide it. LoRa is starting to provide it. Sigfox can't provide over-the-air upgrade. Security, Sigfox doesn't provide any security, it's up to the application layer. LoRa, Wize, roughly equivalent. NB-IoT, better because cellular grade. Standardization, I've put green everywhere except LoRa because LoRa has a non-disclosed physical layer. All other solutions are open. Low cost, okay, Sigfox for sure is the lowest cost solution. LoRa and Wize probably the same cost, roughly, maybe roughly. NB-IoT currently is more expensive in terms of modules and extra. Maybe inbound noise, so the noise in the band. An advantage of Wize is that compared to the 800 MHz band, the Wize band is less noisy currently in Europe than the 800 megahertz band. NB-IoT is even better because it's a cellular band, so it's a managed band by the operator. Okay, and the only way I put on Wize is the worldwide coverage, because currently the Wize frequency band is not worldwide, even if we are working on it in some countries, and it will never be in the US, for example. That's it. So roughly Wize key application, the best application for Wize. So Wize can cover plenty of application, but the best application is indoor and especially deep indoor. And the good news is that there are plenty of applications for indoor and deep indoor. A couple of examples there, but I'm sure you have plenty of other applications in mind. And currently, it's not a surprise that metering applications are for the moment the key application for Wize, because meters are indoor and deep indoor. I have finished my presentation. Time for to give you some time for Q&As. Just to show you my email on the last slide if you want to talk to me. But then we can go back to the questions. I don't know, Alain, do you want to summarize the questions, or do you want to go through the list? Alain? No.
Yes, Robert. Yes, Robert. Yeah. Yes, we have some question. We appreciate your presentation. Thank you. A question from Ryan. Have a firmware update over the year been done on project at large scale? So I think that you have done the response before. Yes.
Yes, and you are the best one, Alain, to confirm that.
Yes, I confirm. We have used, unfortunately, this feature due to a bug in one of our meter, and the last download that we have done targeted more than 50,000 meter, and we download a new firmware on the park in one night. We have also a question of Ryan. Is Wize used in mainland China, not Macau or Hong Kong or Taiwan? Or are there China's metering manufacturers producing Wize device? I know that Suez have a pilot in China, but I don't know really where. I think that the best contact, if you want more information, is Eric Farnier. I give you the email of Eric in the chat.
Maybe there is one Eric in the participants. I don't know if it's a good Eric. Maybe you can give him the microphone.
I think it's Eric Frottet from Itron.
It's not Eric. Okay, so
it's not Eric Farnier.
Okay, sorry.
Also, we have some question. In the Wize protocol, there are backend standard. For the moment, no. Each operator has his own backend, but in the technical committee, we have a topic on this subject, and in the future release of the Wize protocol, we will work on it. Today, there are gateway. A new question. Yes, the gateway are manufactured by Sagemcom and Kerlink, and if other manufacturer want to design this gateway, please contact GRDF or Suez. Maybe more question on the...
Yeah, there is one question here. Why do you rate Wize security at 2 and NB-IoT at 3? Basically because NB-IoT has a mandatory secure element, the SIM card, which provide a secure way to store the security of the device. So for us, this means that NB-IoT provide a little more security than Wize because of this secure element. But we could have this kind of level with Wize 2. How is COVID affecting the ongoing Wize smart market route? I guess that nobody knows.
I can respond for GRDF. I don't know for Suez, but for GRDF, we have rollout right now, as Robert said before, 5.5 million of meter. Since the start of the COVID, we stop the rollout, but we will restart the rollout for May 11. As in France, we start the de-quarantine at this date.
Okay, a question from Ryan for over-the-air upgrade. How much energy does an upgrade consume from the battery? So that's an interesting question. So it depends, of course, on the number of downloads and on the size of the download. So and it's up to the meter manufacturer to implement or not, say, an intelligent upgrade mechanism in order to download some patches and not the full firmware. If we assume that a significant part of the firmware is downloaded, it's something like 10 minutes download usually. And that means that the receiver, so the meter, will have to receive during 10 minutes and maybe 2 or 3 times if we have several download windows. Let's say half an hour of receive activity. Receive activity is maybe 20 milliamps, half an hour, 20 milliamps. It's 10 milliamp hour, which is very small compared to the battery, which is a couple of 2-3 amp hours. So we assume that doing an upgrade every year on a meter through 10 years or 15 years will not be significant in terms of lifetime. But of course, we can't have an upgrade every day. That's it for the question on my side. Any other question from the attendees? Ryan is killing a message, so we have to wait for a couple of seconds. If not, you have to know that there will be thank Ryan. There will be
Thank you, Ryan.
Another session in June. Don't have the date. You have the date, maybe?
16.
So the next 16 of June. This next session will be in French. And if you need another session in English, just let it know to the Alliance, and we will for sure organize follow-up meetings. And this webinar will also be was recorded and will be shared, I guess, on YouTube sometime. Okay, Alain, I'll let you conclude.
Yes, thank you to everybody for your participation. We appreciate, and we will close the webinar. And have a good day, and take care of your love.
Thank you. Goodbye, everybody.
Bye-bye.